So now that we have got an understanding of the symmetrical components, we can analyze the unsymmetrical faults. Right? So first unsymmetrical fault is the single line to ground fault, LG fault it is called. Okay. Another unsymmetrical fault is the line to line fault. Two lines are short circuited. And we also have the double LG fault. So all these three, they are unsymmetrical faults because they are going to induce imbalance into the three-phase system. Okay. Now as I said before, unsymmetrical faults are going to be more commonly occurring as compared to the three-phase faults. Okay. So LG faults will be the most common faults. About 70% of the time the fault is the single line to ground fault. And next highest occurrence is the line to line fault, 15% of times. Okay, so this is just approximate. Okay. Next, double line to ground fault, they occur about 10% of the times. Okay. And finally, we have the three-phase symmetrical fault. So the percentage of occurrence is about 5%. So we will deal with these faults one by one. First, we will consider the single line to ground fault. Now what happens in unsymmetrical faults? The sequence networks, they are going to be interconnected. Okay. So we are going to see what kind of interconnection, how the sequence networks are going to be interconnected with each other for different kinds of faults. That is what is unsymmetrical fault analysis. Okay. So if you take the three lines, let us say these are the three transmission lines, and the fault has occurred somewhere here. Okay. Now when fault occurs, it is a line to ground fault. So what you can take this as, you can take a short circuit or even a fault impedance. Okay. So if there is no fault impedance, simply ZF will be 0. Okay. So now the current through the other two phases, this is going to be 0 because all of the current will now flow through the fault because it is offering a short circuit path, right? So all of the current will now flow through here. So this is going to be the fault current. Here the fault current will flow. Here no current will flow, right? All of the current will pass through here because it is a short circuit. So we can write two relations here. First is IB is equal to IC is equal to 0. Next, what will be the voltage at this point? That is going to be the phase voltage VA will be IF into ZF. So we have two relations here. Okay. So now we can take the symmetrical components of current. So what will that be? IA0, IA1 and IA2. This is the symmetrical components. So A inverse into original phasors. So A inverse we can write as 1 1 1, 1 alpha alpha square, 1 alpha square and alpha. And here the original phasors. So what will be the phase A current? It is going to be the fault current. IB and IC will become 0. Right. So from here you can find out each of the symmetrical currents. What is IA0? This is IF by 3, and IA1 is also IF by 3, IA2 is also IF by 3. So this means that all of the currents are, all of the sequence currents, they are equal. So this is the first clue that we have as to how the sequence networks will be interconnected, right? So this is the first relationship. Now the second one you can get from the voltages. So we know VA is IF into ZF. Now IF you can write in terms of the sequence current. So if you take IA0, 3 IA0 into ZF. Now the voltage you can express as the phasor sum of the sequence components, symmetrical components, right? So this will be the second relation that we have. Now using these two relations, we have to find out a interconnection. What is the kind of interconnection between the sequence networks? So from the first relation you can see that current is equal. All the sequence network currents are equal. That means what? All the sequence networks, they are in series. Okay, and you can see here, if you add the voltages of each of the sequence networks, this is equal to 3 Ia naught ZF. Okay, so here also we see that this is a series connection. So first we will draw the series connected sequence networks. The positive sequence network will have the internal voltage as well, because the transmission line will be driven by some generator, right? And here let us say this is the positive sequence impedance. So this is what? The positive sequence network. The voltage here is VA1 and the current will be flowing out like this, IA1. And next we have the negative sequence network, let us say. So here this impedance is Z2, the current flowing through this is IA2 and the voltage across this will be VA2. And next finally the zero sequence network. This is Z0, here you will have VA0 and here what will be the current? IA0. Now since IA1, IA2 and IA0 they are all equal, we will just connect all of these. Okay. Next, when you add all these three voltages, what is it equal to? 3 Ia0 ZF. Now the current anyways that is flowing is IA0 or IA1 or IA2, it doesn't matter because all three are equal. So you can write as this VA, here you can write VA0 plus VA1 plus VA2, you can write as IA0 because that is the current flowing into 3 times ZF, right? So that means you are going to have a impedance of value 3 times the fault current, so fault impedance, right? So this is 3 ZF, okay, and the current that is flowing through this is IA0 is equal to IA1 is equal to IA2 and this is related to the fault current as IF by 3. You can also mark the sequence networks here, right? This is the positive, this is the negative sequence and this is the zero sequence network. Okay, positive sequence network, negative sequence network and zero sequence network. Now from here how we have to proceed? So now we got the interconnection, now we can use the normal network relations, right? So what will be the current? This is the entire circuit that we have here. What will be the current? This is equal to the internal voltage divided by the entire impedance. What is the entire impedance here? The sum of the sequence impedances plus 3 times ZF. This will give you the current, right? So you can write IA0 is equal to IA1 is equal to IA2. This is equal to EA by Z1 plus Z2 plus ZF plus, sorry, this is Z0 plus 3 times ZF. Okay. Now this is equal to IF by 3. That means what will be the fault current? The fault current IF, this is equal to 3 times the internal voltage divided by Z1 plus Z2 plus Z0 plus 3 ZF. Okay. So this is what we want, right? The expression for fault current. Now once we know the fault current and the sequence components, you can find out everything else, all the voltages as well. So you want to find out the phase voltage. So this is VA0 plus VA1 plus VA2. Now what is VA0? This is equal to minus IA0 into Z0, right? And IA0 will be found from IF by 3, right? So you can write IF by 3 here instead. IF by 3 into Z0, and VA1 is going to be EA minus IF by 3 Z1. and VA2 it is going to be minus IF by 3 into Z2. Okay, so this is how you can find out the phase voltage A. Similarly, VB if you want to find out, this is what VA0 plus alpha square VA1 plus alpha VA2. Similarly, you can write the expression for VC and you can find out. Now we will deal with the line to line fault, LL fault. Okay, so here if you take the transmission lines like this, two of the lines, let us say this is phase A, B and C, and two lines here they are short circuited, B and C, let us say. So here you have the fault impedance ZF. Now what will happen? The current through this IB whatever is there, that will entirely flow through here. So IB will be equal to the fault current. And what about this current? IC. So you can see that IB will flow like this. This will be like a return path, right? So IB is equal to minus IC. So what is the first relation that you have here? IB is equal to minus IC and this is equal to the fault current. Okay. Next, if you see, this voltage will be VB here and this voltage is VC. What will be the potential difference here? VB minus VC is equal to IF into ZF. So this is one relation. VB minus VC is equal to ZF IF. Okay. Now we will take the symmetrical components of the current. So what will we get? IA0, IA1 and IA2. This will be equal to A inverse, which is 1 by 3, 1 1 1, 1 alpha alpha square, 1 alpha square and alpha. And here the currents are going to be IA, which is 0. The other phase currents will become 0 once the fault occurs, right? So IA is 0. And next IB we have, this is equal to the fault current, and IC is equal to the minus of fault current, right? So from here what will you get? IA0, this is what it is equal to IA plus IB plus IC, which is 0. So there will be no zero sequence current. Okay, so when you can see that when there is no ground fault occurring, there is only line to line, there is no ground fault. So when there is no ground fault, the zero sequence current will not flow. Okay. Next, what about IA1? IA1 is equal to 1 by 3, 0 into 1 plus alpha into IF plus alpha square into minus IF. So this you can write as IF by 3 alpha minus alpha square. Okay. And what about IA2? This is going to be 1 by 3 alpha square into IF plus alpha into minus IF. So this will be IF by 3 alpha square minus alpha. Okay, so you can see that IA1 is equal to minus IA2. So this is one important relationship that we will be needing in order to find what will be the interconnection, what is the kind of interconnection between the sequence networks. We will also write this fault current here, right? So this is equal to what? IF by 3 alpha minus alpha square. So this is the first relation. Next we will make of this relation, VB minus VC is ZF into IF. So here I am just repeating this, VB minus VC is IF ZF. We will express the voltages, these original phasors, in terms of the symmetrical components. So what will this become? VB is VA0 plus alpha square VA1 plus alpha VA2 minus VC we can write as VA0 plus alpha VA1 plus alpha square VA2. This is equal to IF ZF. So here you are going to get VA1 minus VA2 into alpha square minus alpha. This is equal to IF ZF. Now IF the fault current you can write in terms of the symmetrical currents, right. So, we will do that. This gives you VA1 minus VA2 into alpha square minus alpha. This is equal to ZF, we will take out like this. IF you can write as 3 by alpha minus alpha square into IA1. Okay. So, this if you simplify, you are going to get VA1 minus VA2 is equal to IA1 ZF. Okay. So, this is after the simplification. Now, this is the second relation that we require to get the sequence network interconnection. So, we will now see what is this interconnection. Now, you have to understand that the zero sequence current, we got it as 0, that means no zero sequence current will flow. So, we do not have to include the zero sequence network, we are only concerned with the positive and the negative sequence. So, this is what? This is the positive sequence network. This current will be IA1 and this voltage is going to be VA1. And similarly, you will have, this is positive sequence impedance, here negative sequence impedance is Z2. Okay. So, now this is the current flowing out of this is IA2 and the voltage across this is VA2. Now, if you remember the first relationship, what is that? IA1 is equal to minus IA2, that means there is a connection here. Okay. Now, second relation, if you see VA1 minus VA2, so potential at this point minus potential at this point is equal to this voltage drop. Okay. So, that means there is an impedance here of value ZF. Okay. So, in this way both the relations are now satisfied. So, this is how you can take IA2, this is equal to what? Minus IA1. Okay. So, this is the sequence network that we need for the line to line fault. Now, once we get this network, then what we can do? We can write the expression for the fault current, right. First we will take the sequence current, IA1 will be what? It is equal to the internal voltage divided by the total impedances which are in series, right. Z1 plus Z2 plus ZF. Now, what will be the fault current? IF. This is equal to 3 times IA1 divided by alpha minus alpha square. So, you can substitute this equation here, alpha minus alpha square into this expression. Okay. So, you are going to get EA divided by Z1 plus Z2 plus ZF. So, then the final expression, if you simplify, you are going to get J root 3 EA divided by Z1 plus Z2 plus ZF. Okay. So, this is the fault current. IF is J root 3 EA by Z1 plus Z2 plus ZF. What will happen if there is no fault impedance? Simply divided by Z1 plus Z2. Okay. And from here you can find out the voltages as well. If you take VA, this is what? VA0 plus VA1 plus VA2. Now, VA0 anyways it is 0, right, there is no zero sequence network, and VA1 it is EA minus IA1 Z1 plus VA2 is minus IA2 Z2. IA1 and IA2 you can find from the fault current, and rest values will be given, so you can find out the voltage. Similarly, VB and VC you can find. Okay. Double line to ground fault. So, here two lines are going to be short circuited to the ground. Okay. So, if you take the transmission line, now two of the lines they will be short circuited and also they will be connected to the ground via a fault impedance ZF. What will be the current here? The fault current. Okay. So, now if this current is IB, let us take this phase as A, B and C. So IA anyways it will become 0, and IB is here, IC is here. Okay. So you can see that IB and IC both will go towards the fault current. Okay. So one relation you can write here, IB plus IC, this is equal to the fault current. And what do we have about the voltages? The phase voltage VB is equal to phase voltage C, right, VC, and this will be what? It will be equal to the voltage drop across this. So IF into ZF. Okay, so we will start off with these two relations. Also another relation is IA is 0. Okay, so these three relations, with using these we can find out the interconnection of sequence networks. First we will consider this last relation. Okay, so IA is equal to 0 implies that IA0 plus IA1 plus IA2 will be 0. We have expressed the phasor, this original phasor, in terms of the symmetrical components. Okay, so this is the first relationship that we want. Next, if you consider the next current relation, IB plus IC is IF. So what will happen here? IB plus IC is equal to IF. This also, if you represent in terms of symmetrical components, what will you get? IA0 plus alpha square IA1 plus alpha IA2 plus IA0 plus alpha IA1 plus alpha square IA2. This is equal to the fault current. Okay. So this, if you simplify, what you are going to get? 2 times IA0 plus alpha square plus alpha IA1 plus IA2. This is equal to the fault current. Now IA1 plus IA2 is what? It is equal to minus IA0 from this first relation, and also alpha square plus alpha is minus 1. Why? Because 1 plus alpha square is 0. You can verify it later. Okay. So this final expression you are going to get 3 times IA0 is equal to fault current. That means IA0 is equal to IF by 3. Okay. So this is the second relation. Next we will consider the symmetrical components of voltages. Okay. So you can write the symmetrical components as A inverse, which is 1 by 3, 1 1 1, 1 alpha square alpha, 1 alpha and alpha square, and this is going to be VA, VB and VC. Okay, but VB and VC, they are equal. Okay, so here you are going to get VA0, this will be what? 1 by 3 VA plus 2 VB you can write. Okay, because VB is equal to VC, because VB is equal to VC. Now this is the third relation. And what about VA1 and VA2? VA1 you can write as 1 by 3 VA plus alpha square VB plus alpha VB, right? So here you are going to get 1 by 3 VA minus VB. Similarly, VA2 also you are going to get 1 by 3 VA minus VB. Okay. So this implies that VA1 is equal to VA2, which is equal to 1 by 3 VA minus VB. So now this equation is equation 4. Now what you are going to do is, you have to solve this equation 3 and equation 4 for the two unknown variables VA and VB. So solving equation 3 and 4 for VA and or only VB. VB is enough for us. For VB, we get VB is equal to VA0 minus VA1. Okay. Now once again, VA0 minus VA1, what is VB? Here we have this relation, VB is equal to VC is equal to IF ZF, right? So we will substitute this IF ZF here, this is equal to IF ZF. Now IF you can write as 3 times I A naught, right? So this will become V A naught minus V A1 is equal to 3 I A naught Z F. This is the final relation. Now we will draw the sequence networks first. First, the positive sequence network. This is what? Z1. The current flowing out of this is IA1 and here you have voltage VA1. Next we have the negative sequence network. This is what? The current coming out of this is IA2 and this voltage is VA2. And finally the ground zero sequence network. This is going to be Z0, current flowing out of this is IA0 and this voltage is VA0. So we will start with interconnecting the positive and negative sequence first. Okay. So what is the relationship here? You have in equation 4 VA1 is equal to VA2. That means both these they should be in parallel. Then only the voltages will be equal, right? So these two you can connect here. Okay. Now here you have to understand this current will be here IA2. Okay. So here we got the connection between positive and negative sequence. Now we will try to interconnect this with the zero sequence network. So if you see the last relation VA0 minus VA1, this is what? It is equal to 3A0 ZF. So what is VA1? This is here across this and VA0 is across this. So between this and this point the potential drop is 3IA0 ZF. Okay. So first we will draw, there is one impedance element here, right? This will be like this. So this is the interconnection here. So we will complete this circuit. It is going to be like this. Now what about this? The current is going to flow on this side. This is IA0. Okay. So now the current flowing through this impedance element is I0, but the drop across this should be 3 times IA0 ZF. That means the impedance value is 3 ZF. So this is the final circuit. Now what is the fault current? Our final goal is to find the fault current, right? So IF is equal to 3 times IA0. Okay. So now using this circuit we have to find IA0. Okay. So first we can find IA1. What will this be? This will be equal to the voltage EA divided by Z1 plus this is what? Z2, right? Z1 plus Z2 parallel to Z0 plus 3 ZF, and then IA0 you can find by current division rule, right? So according to current division rule you will get this impedance divided by sum of this and this impedance into the total current, right? So this will be Z2 divided by Z2 plus Z0 plus 3 ZF into IA1. Okay. So once you find IA0 then you can find out the fault current and the phase voltages also you can find out. Okay.